Right, good morning all. I hope everyone can hear me okay. And if you can't, please wave or shout out. So my name is Paul Willis. I'm a hazardous chemical expert and a fire and explosion investigator within the Hawkins Marine team. I've been with Hawkins for about 10 years, and before that I was with Burgoyne. This morning I'm going to spend about 35 minutes going over the safety issues surrounding the transportation of coal by sea, what can be done to mitigate the risk, and how to recover from a deteriorating cargo condition. I primarily work with P&I clubs and their members to provide safety advice prior to loading. I can also assist member crews remotely to manage and attempt to control deteriorating cargo, and, if required, attend the vessel to provide close support and advise on the control measures needed if things start to go wrong. So in simple terms, coal is made up of plant material, bog and marsh weeds that has been covered by sediment and subject to heat and pressure for around 20 to 300 million years. The type and quality of the coal will be dependent on several factors, including the type of the source plant material, the depth, and the age of the deposit. Coal quality is generally referred to as rank, with a low rank coal being lignite, which is soft, has relatively low density, and it appears dull and flaky. This type of coal is porous and can be full of volatile organic compounds, such as methane. At the other end of the scale is anthracite, which is a high rank coal. It is hard, dense, and has a shiny appearance. Generally, but not always, the high rank coals have a lower VOC content. World coal extraction is slowing, but it's still huge at around 7.7 billion tonnes per year. The majority of coal extracted is low rank and used for power generation. One primary producer is Indonesia, and in particular the Kalimantan region, which is known for its shallow deposits of relatively young, low-rank steam coal. This is shipped to India and Southeast Asia to keep the lights on. From the open cut mines, the coal is moved to vast storage areas on land. Sometimes the coal is not held for long in these areas before being shipped, and this can be problematic because freshly mined coal is more reactive than similar coal, which has been left to weather for months in the open, because it's been locked up underground for millions of years away from oxygen. Coal is typically shipped in bulk carriers, with a load being in the region of 100,000 metric tonnes. The low rank coal mining areas of Indonesia often don't have deep berths to accommodate these large vessels to allow them to be loaded directly from the shore. In particular, the Kalimantan region has very limited deep water facilities. The bulk carriers will normally be held at anchorage, and barges are used to ferry the coal from storage berths to the deep water anchorage, where grab cranes, either on floating platforms or mounted on the ship, then load the vessels. It's not uncommon to see dozens of loaded barges in the anchorage area for days or weeks before being discharged into bulk carriers. This can be the start of problems with the coal, as the barges are subject to heat from the sun, wind and rain, all of which can begin the deterioration of the coal. This is the ship I was on in Navalaki, India, where I spent a week on board monitoring the cargo conditions every few hours during discharge. It was very slow as there was only one floating crane available. This is another vessel I spent some time on in Vietnam. This one was fitted with self-loading cranes, which made the discharge a bit faster. So what are the hazards? We have liquefaction. So this causes stability issues. It's not something I've ever come across, but I understand it can happen. Corrosion. This obviously damages the hull of the ship and the cargo holds. Other more significant safety issues are volatile flammable gases emitted from the coal, i.e. methane, which presents an explosion risk. Then there is also the depletion of oxygen in the hold, which causes a danger of asphyxiation to the crew or any person entering the hold. And self-heating. Now this can emit toxic gases such as carbon monoxide and hydrogen sulfide and can lead to fire in the hold. So the International Maritime Solid Bulk Cargo Code requires vessels shipping coal to have equipment on board capable of detecting and monitoring oxygen, carbon monoxide, and flammable gas. Most will also have a hydrogen sulfide sensor in the gas detector. There are two types of flammable sensor, catalytic and infrared, which I'll discuss in a little more detail later. IMSBC also requires vessels to monitor the pH of bilge water and the temperature of the cargo. So corrosion is linked to the sulfur content of the coal. 0.3% is deemed to be low, with 4% sulfur considered high. These soluble sulfur compounds can dissolve in water, such as rainwater from when the cargo is on the barge, and form sulfur acids, and these can drain into the bilges. Crews are advised to monitor the bilge water's pH and pump it out if necessary. In terms of gas detection, most coal-carrying ships carry portable electronic devices. They use a wet chemistry cell to detect the presence of oxygen, carbon monoxide, and hydrogen sulfide. The detectors on most ships will be fitted with a catalytic flammable gas sensor. Our gas detectors, the Draeger XAM 7000 on the left and the XAM 8000 on the right, are fitted with both catalytic and infrared flammable gas sensors. Using these tools, we're looking to mitigate the risk of explosion, of fire, and to prevent the toxic effects of a rogue cargo. Dealing with toxic gases first. Carbon monoxide and hydrogen sulfide can both be emitted from the coal. They're both toxic at relatively low concentrations, with the short-term exposure limits, that's the time at which a human can stand to be there without any toxic effects, being 100 parts per million for CO and 10 parts per million for hydrogen sulfide. Nothing good will happen if you breathe in concentrations at or above this level. Carbon monoxide is a particular issue because it's odourless and it can migrate from cargo holds into the accommodation section of the ship. In addition to being toxic, carbon monoxide and hydrogen sulfide are both flammable and therefore could produce an explosive atmosphere. But in my experience, it's very unlikely a coal cargo will produce a flammable atmosphere of either of these gases. Methane, on the other hand, is commonly emitted from coal cargoes in quantities which could be flammable and therefore explosive. I'll come on to what the flammable range means shortly. So going back to gas detection equipment, this is a basic schematic of a catalytic type flammable gas sensor. Inside the sensor, there are two electrically connected platinum wire coils, here and here, both embedded in two separate porous ceramic beads. One, the active bead, is covered with a catalyst. The other one isn't. When operating, both of the wire coils are heated electrically. When flammable hydrocarbon gas like methane enters the sensor, it reacts and oxidizes on the bead of the catalyst. In simple terms, it burns. Nothing happens on the other bead. The heat generated on the active bead alters the electrical resistance of the coil in it, and an electronic arrangement called a Wheatstone bridge allows that change in resistance between the two coils to be measured and then displayed on the gas detector screen as a concentration of gas. Importantly, the catalytic sensor does not work if the oxygen level is below 10%. It is also prone to poisoning by compounds such as silicones. This is a schematic of an infrared flammable gas sensor. There are two main components, one being an infrared light source, the other being an infrared detector. The sensor operates on the principle that carbon-hydrogen bonds present in the hydrocarbons absorb infrared. When a gas such as methane enters the cell, the detector measures a reduction in the amount of infrared reaching it, and electronics convert this to a digital display of the gas concentration. This type of sensor will work in low or zero oxygen environments and is not prone to poisoning, but it will not detect acetylene or hydrogen, and it is quite expensive. When a cargo is loaded on the ship, the declaration presented with the cargo should identify whether or not the coal is a methane emitter, but this documentation is not always reliable. Earlier I mentioned about the flammable range. This is the range at which a flammable gas can burn in 20.9% oxygen, i.e. normal atmospheric oxygen. This range has two boundaries. The LEL is the lower explosive limit. Below this concentration, there is not enough gas to ignite. And the UEL, upper explosive limit, above which there is too much gas to ignite. Methane has a lower explosive limit of 5% by volume. Therefore, we call that 100% of the LEL. Here we can see graphically how the explosive limit looks. The explosive range of methane is between 5 to 15% by volume, which means on this chart it's only explosive in this red zone. When we measure the percentage LEL, we're only looking at the yellow zone and measuring how close we're getting to the red danger zone. So 50% LEL is here, and this is equivalent to 2.5% by volume of methane. And 100% LEL is here, and is equivalent to 5% by volume of methane. Normally, LEL is based on 20.9% oxygen, i.e. a normal atmosphere. If there is a decrease in the oxygen concentration, this will have the effect of reducing the flammable range by increasing the LEL and decreasing the UEL. Coal can consume oxygen in the cargo, so catalytic sensors can be a problem when dealing with a road cargo. An infrared flammables detector is much better, as it can be set to percentage volume reading rather than LEL, and then a numerical calculation can be made to determine the explosive risk relative to the oxygen concentration. The IMSBC is very clear on the crew's post-loading actions with regard to methane. After loading, they should ventilate the cargo for 24 hours. They should then stop ventilation for 4 hours, then monitor the gases in the hold. If the LEL is found to be more than 20%, then they should ventilate for 4 hours. Stop ventilation for 4 hours to let the gases stabilise in the hold before monitoring again. If the LEL is still high, then repeat this process until it is reduced to safe levels. The purpose of ventilation is to try and get rid of the methane. The problem is doing that introduces fresh air and oxygen and promotes self-heating. With some coals, it can be a very fine balance between preventing an explosion and causing a fire. We want to try and find the sweet spot of a low LEL, a low O2, and a stable CO reading, and ride that point throughout the voyage. Some of the carbon in coal is reactive, and so wants to combine with atmospheric oxygen. Oxygen depletion in the cargo hold is essential to preventing self-heating of the cargo running out of control. The danger here is the safety of the crew, i.e. it is not safe to enter a hold containing coal without gas monitoring equipment and possibly breathing apparatus. Self-heating. This might be declared on the cargo documentation, but don't rely on it. Some coals, especially the low-rank coals from Indonesia, will self-heat when exposed to atmospheric oxygen, and they will catch fire if left exposed to it in bulk quantities. So what is self-heating? In basic terms, self-heating is the oxidation of carbon-carbon double bonds. Firstly, we'll have a closer look at the atomic structure of coal. So coal is a complex polyaromatic hydrocarbon with furan, amine, carboxylic acid, hydroxide, ketone, and organosulfur functional groups. In this representation, reactive carbon double bonds are shown as rings. There are lots of them. So coal plus oxygen in the presence of water can form a complex referred to as oxycoal. This oxycoal is an equilibrium state, i.e. the reaction of the oxycoal formation can go both backwards and forwards depending on the conditions. It's not particularly well understood and it's very difficult to study. Factors that play a significant part in determining how coal will react in terms of self-heating are the age of the coal, both geologically and in terms of how long ago it was extracted. Younger and less weathered coal is more reactive. The moisture content, the insulation factor, i.e. the size of the load. A single bag of coal is very unlikely to self-heat. However, 40,000 metric tons in a cargo hold is possible. The quantity of the fines. More fines means more surface area and more reactive area. Another factor is the air/wind exposure. Cast your mind back to the earlier slide showing the coal barge anchorage in Indonesia. That barge could have sat for days or weeks in the raging sun, occasionally getting rained on and with a stiff breeze. These are ideal conditions to promote the self-heating within that load. So, oxidation of coal produces heat. In sufficiently large mass, this heat can be contained and promote further oxidation of the load in a positive feedback runaway reaction. A crew should use an infrared thermometer to measure the temperature of the coal as it is being loaded very regularly. If any part of the load is found to be more than 55 degrees C, centigrade, it should be rejected because it has already begun to self-heat. To minimize self-heating, the best course of action is to prevent oxygen reaching the cargo. A well-sealed hold is essential, as is appropriate ventilation to hit that sweet spot of the LEL being below 20%, the CO being stable, and the O2 being low. If the carbon monoxide is increasing, self-heating is occurring. An often overlooked factor with coal cargoes is the importance of trimming the cargo. Poorly trimmed cargo has a much larger surface area exposed to the atmosphere due to the sloping sides. Without exception, the coal fire cases that I have been to have inevitably been in the corners of the holds under the deck where the cargo is not trimmed and there is a slope of exposed cargo surface. Minimizing the surface area is essential. So what to do when it goes wrong? If there is self-heating and high LEL, this is the worst case scenario. Most crews will be well out of their depth dealing with this situation. Ask for help from an expert and probably for an attendant. If there is no methane, seal the hold well with bitumastic tape such as ram neck to prevent oxygen reaching the cargo through gaps within the hatch covers. Eventually the O2 will be depleted and the reaction will stop and the cargo will cool. So this is an example of gas results from a good cargo with readings taken about 4-hour intervals. So after 24 hours, the ventilation has been stopped and then readings are taken at 4 hours. As you can see here, the oxygen level in green is decreasing nicely, but the LEL level in red is increasing. So we need to ventilate for 4 hours and then close for 4 hours and monitor. We see the O2 goes up and then the LEL goes down during ventilation. This cycle is repeated and eventually there is a steady rise in the CO in blue because we have allowed enough oxygen for the self-heating to become an issue. Now is the critical time to ventilate appropriately to ride that sweet spot. We don't want to let the self-heating get established, but we also need to get rid of the methane. As you can see here, this is achieved by eventually, and the methane stabilizes at a low level, and there is no need to ventilate anymore. Each of the rises in oxygen corresponds to a period of ventilation, with the drop in oxygen corresponding to a close in ventilation. Eventually, we reach a point where the O2 begins to drop rapidly and the CO stabilizes. This is because the self-heating is stopping. This is what it can look like when self-heating has got out of control, a hold full of smoke. And here's a thermal image of that same cargo hold, showing the hot spots in the cargo under the layer of smoke. So what to do in this situation? Advice will depend on the specific case, but one thing that we can do is apply small amounts of fresh water, not seawater, in a targeted approach. This is why we carry a thermal camera, so we can direct the crew to where to apply water. We are always cautious and aware of the risk of a steam explosion and the loss of visibility caused by large quantities of steam being produced. The reason we don't recommend the use of seawater is because contaminated cargo could be rejected due to the corrosion risk from salt to the end users' boilers and furnaces. Here's an example of a targeted approach using thermal image cameras to locate hotspots and douse them with fresh water. This should be done safely where BA is used if there is CO or hydrogen sulfide present. You need to be very careful of these short-term and long-term exposure limits. If the stevedores won't work a hold to discharge and you can't put the fires out, the next best option is to seal the hatch covers and starve the self-heating of oxygen. This could mean quite a few weeks of delays monitoring the O2 and CO levels at anchorage, waiting for the fire to extinguish. As a very much last resort, we might recommend flooding the hold. Normally, when the fire is very severe and could compromise the hull. It's a last resort. Flooding introduces stability issues. The cargo may well be rejected as seawater damage, and inevitably there will be delays. The shipper's cardinal rule is to follow IMSBC code provisions, and if in doubt, ask an expert for advice. So that's the end of my introduction to carriage of coal and the hazards. So following on from Nick Carey's talk earlier this week on the science of cargo self-heating reactions within shipping containers, my colleague Ed will be giving a fascinating insight into some of the other causes of container and container ship fires. If you can, please join. So if anyone has any questions, please feel free to raise a hand and I'll try and answer it, or alternatively send me an email and I will get back to you.